Good evening, everyone. Welcome to this tutorial lecture on uh, discrete mathematics. So this week 7, and this week we'll be again discussing assignment problems from previous iteration of this course, and our focus for this week will be on graphs. So I'll start sharing my screen. I hope the screen is visible to you. Okay, so let us get started. So coming to the first question for our discussion. So which of the following is a graphic degree sequence? So before solving the question, so let us just revise what is degree. So can anyone tell me what is degree of a node in a graph? Anyone?
One node is connected to how many nodes? This is called degree.
Right, you're absolutely right. So degree is basically number of edges linked to a node in a graph. So degree sequence is nothing but a sequence of the degrees of nodes in a graph. So what does that mean? So let's say you have this graph. Let me draw one graph, and let's say like this. So let's call this node A, B, C, D. So the degree of node A is 3, of B is 2, of C is 3, and D is 2. So the degree sequence is uh, DS. I'll call it. It's 3 2 3 2. So you degree sequence need not be in any order. Need not be in any specific order. So this could be a degree sequence. Also you can start at B and you can write 2 3 2 3. This is also right. Or you can simply write 2 2 3 3. This is also right. So basically it's just a list of the degrees of a node. So now coming to the question, what is a graphic degree sequence? Now graphic degree sequence is a special type of sequence is where given the degree sequence, it's it is possible to construct a graph from the sequence. So that is a graphic degree sequence. Now give you two examples and ask you that whether they are valid degree sequences or not. So if you have the sequence 2 2 2, what do you think? Is it a graphic degree sequence or not? Anyone?
Yes, it is a graphic degree sequence because it forms a triangle.
Right, you're absolutely right. So it is a graphic degree sequence, and you can, like you said, we can form a triangle like this. So it is 2 2 2. We have a triangle. But if we have, let's say, 1 1 1, so we have, let's say, 3 nodes. So the number of elements in the sequence is the number of nodes. So can we create a graphic sequence from this 1 1 1?
No,
Right. So we cannot create a sequence because suppose I connect the first one to, let's say, the left one, then the left one I is already has gets a degree of 1, and similarly we cannot connect anyone to the first one because its degree is 1. So the outgoing edge from the third node is cannot be connected to any of this node, but that is but since there are no nodes in the graph present, so this sequence cannot be possible. So now coming to this question, so which of this represents a graphic degree sequence? How will we check it? So to do that, we have this wait, okay, to check graphic sequence, to check uh, graphic degree sequence, we have an algorithm called the Havel Hakimi algorithm. So what we do is basically suppose uh, okay, so what we do is, let's say we pick option A. So let me write it down: 6655 432. So you have this sequence: 6655 432. Okay, so the sequence is like this as follows. So what we do is, how many nodes are there in the graph first? So is the number of elements in the sequence. So we have 3 3 7. So let us construct 7 nodes: 1 2 3 4 5 6 7. So now what we do is, we first step is arrange arrange in descending order. Remember that the degree sequence itself need not be in any order, but for the Havel Hakimi algorithm to work, we'll have to cast it in a descending order. So we arrange it in descending order, so it's already given in descending order, we don't have to do anything. Numbers, we take the highest element, we remove the highest element, that is 6 will be removed, and we subtract 1 from the remaining m nodes. So we remove the highest element with degree m. So first we remove the highest element. So the highest element has degree 6, as you can see, and we subtract 1 from the remaining m node. So m we means from the remaining 6 nodes, and then we keep on repeating the process. So what it basically intuitively is like this. So you have picked the first node, we call it a b c d e f g, and we, let's say, call it 6a 6b c d e f g. Now from arrange in descending order. Why it is done, I'll explain to you. So we remove the highest, and so what we do is basically we pick the node a with the highest degree, and we connect the node a with m element. So it is 6, so we connect node a with the next 6 elements. So basically we connected it in order. We connect first to b, then to c, then to d, then to e, we have 1 2 3, then to f, and then to g. All right, now that is why we that is step 2 done. Now we subtract m from the remaining m nodes. So because why we are subtracting, because we have already one edge incoming from this node with the highest degree. So already the degrees of uh, b has been updated to 1. So we are basically trying to create a graph. So now after this, when we connect edges from the node with the highest degree, the other nodes already gain a degree of 1. Therefore we subtract 1 from the remaining m nodes. So the remaining 6 nodes that it were connected, so their degrees have been reduced to 1. So basically now the sequence becomes, so we become star a, and then it is 5b, 4c, 4d, 3e, 2f, and 1g. So this is, so we star because we have created a graph where we have given the first node with 6. So now we'll have to allocate 5 more edges to this node b. So we'll have to give an additional degree of 5 to b. So to do that, so why is it arranging in sequence is because so that we can remove this, we can maintain the order in which we are subtracting 1. So if they were not in descending order, we wouldn't have, in step 3 we'll have to keep track from which nodes the to which nodes the edges were connected, and therefore this remaining m nodes part won't be valid. Therefore we are arranging first in descending sequence and then removing the highest and then subtracting 1 from the remaining m nodes. So now we'll have to connect 5 extra edges to b. So again we do it in sequence: b to c1, c to d, b to d, 1 2 3 4 5. So b is done. So what we do is we put star and we remove 1 from the remaining 5 nodes. So we have remaining 5, so we have, this becomes 3, this also becomes 3. Okay, I'll write it in separate steps so that it's easy to follow. So this next step becomes star a, it becomes b, then we have 3c, we have 3d, we have 2e, 1f, and 0g. So it means that we do not have to add any more edges to this node g. Now now we'll have to add 3 more edges to um, this node c. So again we, let us do it in order: c to d1, c to e1, and c to f1. Okay, so it becomes star a, star star c. We remove uh, 1 from, so it's 2D, 1E and 0F, and 0G will remain. So we are not connecting anything to D. Now from 2D we'll have to give additional two links to D. So we give one to E, but there is 0F, so we cannot put, so we have to uh, give out two edges, two extra edges from D to the remaining nodes. So the remaining nodes after D are E, F and G. We have to uh, so D has to get an additional degree of 2, but only E is available to take one edge. F and G, since their values have reduced to 0, F and G cannot take any extra node. So therefore we cannot produce one more extra edge out from D. So therefore this sequence is not a graphic sequence. So because up till uh, E we can fulfill, so if I up till, so if I remove this dotted line, you'll see that up till E, so these nodes I'll mark them. So A, B, C, E, F and G, their degrees are satisfied. So given this degree sequence 6655432, their degrees are satisfied, but for D not satisfied. So I'll, let's say, mark, color it in red, not satisfied. So therefore it is not a degree sequence, a valid degree sequence. So this is how you check the Havel Hakimi algorithm. So for that, you, if you do it for all the four sequences that are given, you will find that option B is the only correct answer, and you will have, you will get an error in all the other three cases. I i i think it is clear to you guys. So if you try it out on your own, you can see why option B holds correct, and all the other A, C and D will not give you a correct graphic degree sequence. So if you have any doubt, you can ask me now, or we'll proceed on to the next question. All right, let us move on to the next question. So consider the following two statements uh, and choose the correct option. So you have, in a graph, if there is a trail from node A to B, there is always a path from node A to B, and a circuit can never contain a cycle. So just for revision, what is a trail? A trail, in a trail, vertices can repeat, edges can't. Path, neither vertices nor edges repeat. A circuit is a closed trail, and a cycle is a closed path. Now try to answer this question. If there is a graph, if there is a, in a graph, if there is a trail from A to B, there is always a path from node A to node B. What do you think of statement 1? Is it true or false? Anyone? So I'll give you an example. So let's say you have this, let's say 4. Now you create a trail. So let us name them A, B, C, D, E, F. Now in a trail, a node, the vertices can repeat, but the uh, edges can't. So we create a trail, let's say from A to B. So we have A, uh, B, uh, D to B, and E, and then to F. Now this is a trail. So what do you think, that is there a path in this trail? Anyone? So we have this, I'll write it here. So it is A, B, C, D, B, E, F. So this is the given trail. So is there a path inside this trail? uh, Hello, I think you are not audible.
No, it is not a path because B is repeating.
Right, it is not a path, it is a trail. So I am asking, is there a path inside this trail? Can we locate a path that is inside this trail? So Akanksha says that yes, there is a path A, B, E, F. So you go from A to, so the path is, you're saying, let me take a different ink. So you go from A, B, E, F, right? So this is definitely a path that you have. So basically, if you check in this trail, the vertices that are repeating, so from here to here, this forms a cycle, and you can always remove such a cycle or a circuit it can form, and you can get a path straight away. So a trail will always contain a path. So statement 1 is true. Now statement 2, a circuit can never contain a cycle. Is this true? A circuit is basically a closed trail, like I have mentioned here, and a cycle is a closed path. So a circuit can never contain a cycle. Is that true? What do you think of statement 2? Okay, I'll show you with an example. Take the same figure. So we have A, B, C, D, E, and F. A, B, C, D, E, F. Now I'll create a circuit. So a circuit is like a closed path. So we go from A to B, B to C, uh, C to D, D to B, from B to E, and from E again to A. So this is the circuit. So you have A to B to C to D to B to E to A. So this is a circuit. Now does this contain a cycle? Anyone? So can you observe a cycle in this circuit? Is it present or not? Anyone? Right, A, B, E. So A, A, B, E, and A. So you'll have to write A, B, E, and A. So since cycle means the starting and the ending node should be the same. So this is a cycle that is present in the, again, this is also another cycle. So from B, C, D, B, that is also a cycle. So cycles are all can be present in circuits. So this statement, a circuit can never contain a cycle, is wrong. So the right answer is statement 1 is true and statement 2 is false. All right, let us move on to the next question. So coming to the next question, there are 15 employees in an office. One employee, Manoj, wants to create a social networking platform exclusively for him and his colleagues. Employees can choose if they want to add a colleague or not at any point in time. Will there be a situation that each employee is friends with exactly 9 of their colleagues? Is it possible? Okay, someone is asking that a circuit always contain a cycle. Yeah, the right answer is this. A circuit always contains a cycle. Just like a trail always contains a path, a circuit always contains a cycle. Okay. Okay. So moving on to question 3. So is it possible that there are 15 employees and will there be a situation where each of them is connected to exactly 9 colleagues? What do you think of this question? Is it possible? We have 15 employees and each one is connected to 9. So for this question, recall the handshaking lemma. What does the handshaking lemma tells you? Anyone? Can anyone
Sum
tell
of
what it?
all degrees is twice the number of edges.
Yeah, so degrees is twice the number of edges, but that is not exactly the handshaking lemma. So uh, it is related to what you said. So can you take a guess what it is? So I'll tell you. So it is basically that there are uh, even number of odd degree nodes. So what does this mean? That like Akanksha said that uh, there will the degree, let's say number of edges is E. So sum of degree is basically 2 times the number of edges. This is what Akanksha said. So what this handshaking lemma is saying that the sum of degrees is always even. It means that what it means that we can have even plus we can have degrees that where all nodes are, this sum has to be even. So it could be like 2 4 6, then we are getting even. But if we have, let's say, 1 3 8, so this is also even. But 1 3 9, this is odd. But the sum of degree must always be even, because it's twice the number of edges, so it's always a even number, so it cannot be odd. So either that there are no odd number of there are no nodes with odd degree, or there are nodes with odd degree but there are even number of odd degree nodes. So here there are two odd degree nodes, so such that the sum of degree will always be even. So this is the handshaking lemma. So this question is a straightforward question. So it says that, will there be a situation where 15 employees and each of them has 9 friends? So employees are the nodes, and the degree of the node is 9, so it is an odd number. So it says that that a graph should always have even number of odd degree nodes, but there are 15 nodes, so not even, and this is odd degree, that is 9. So by handshaking lemma this is never possible, so the right answer is no. What this means is that, suppose there were 15 employees and each had 9 uh, degree, so the sum of degree would be 9 into 15, that is 135, and edges, so the number of edges would be half of that. This is 67.5, so there will be an it is not an integer. Edges can only be exist in basically natural number, so you cannot have half edge. So you have either one full edge or no edge, so there is no half edge, so there cannot be 67.5 integers. So therefore by handshaking lemma it is never possible that 15 employees with each having 9 uh, connected to 9, exactly 9 friends. So this is not possible. I hope this is clear to everyone. If you have any doubt you can ask, or you can ask at the end as well. All right, let us move on to the next question. Is it possible that a subgraph of a graph is neither spanning nor induced? So can anyone tell me what is meant by a spanning subgraph and an induced subgraph? Anyone? Can anyone tell me what is a spanning subgraph?
Sir, in spanning subgraph, all the vertices of the original graph are included, and in
Right.
induced, the subset of the vertices selected, all the edges which are incident on the original graph on those vertices, all those edges should be present in
Yeah,
the.
perfect. So that is the right answer. So I'll write it down. So spanning subgraph is contains all the vertices of original graph, and induced subgraph contains all the edges associated with the vertices in the subgraph, with the vertices in the subgraph from the original graph. So I'll give you an example. So you have, let's say you have this. So you have, let me create this graph. Okay, so a spanning subgraph would be, so you have all the, you'll have to take all the four vertices, and you can create something like this. This is spanning. And induced would basically be, you take 1 2 3, so and put, so basically you take, I call it a b c d, f a b c d and a b d. So this is induced. So in spanning, you'll have to include all the four a b c d in the subgraph, and in induced subgraph you can take any subset of vertices. Let's say you pick abd, but you'll have to include all the edges that are connected among abd, that is present from the original graph. So this is the original graph. So you see there is an edge between a and b, we put an edge between a and b. It's there's between b and d, we put a edge between b and d, and there is an edge between a and d, we put an edge between a and d. So this is a induced subgraph. Now the coming to the question, is it possible that a subgraph of a graph is neither spanning nor induced? So if I create a graph, let's say like this, we have this. So I take b, d and c, and I connect C and D and B and C, and I leave out B and D, which is actually present in the original graph. So what do you think? Is it induced or spanning?
Sir, it's neither induced nor spanning.
Right. So it is neither induced nor spanning. Nor. So that answers our question, that is it possible that a subgraph is neither induced nor spanning? Yes, we have seen an example, so it is possible. Option A is the right answer. Now coming to question number 5. Is it possible to create a tree which has 7 vertices where the sum of degrees of all the vertices is 14? So now think of a tree. So tree, what is a tree? Every node has one connect, one parent basically. This is the definition of a tree basically. So you have, let's say, a root node. You have, it can have many children, but there will be only one parent. So you can have 3 from here. So this is example of a tree. This is an example of a, so we have how many, let's say I call it a b c d e f g h. So we have how many, 8 nodes. How many edges do you think this uh, tree has? 8 nodes, and edges equal to how many edges? 7, right? So a tree with m nodes has how many edges in general? what is the, for a general tree with m number of nodes, how many edges does the tree have? M minus 1, right? So a tree will always have m minus 1 edges. So it's unlike a graph where it can be varying. A tree with m nodes will always have m minus 1 edges. So therefore sum of degree would be twice m minus 1. So now a tree which has 7 vertices, for this sum of, so it will have edges equal to 6 because m minus 1. Therefore sum of edges equal to 12. But they are saying, is it possible that there is 14? So it is not possible, then it won't remain a tree. So the answer is option B, no. So it is not possible. I hope this is clear. It is pretty straightforward. Okay, come to question number 6. Let G be a connected graph on M vertices. What is the maximum possible number of cut edges in the graph G? So what is the definition of a cut edge? So I will give you an example of what a cut edge is. A, B, C, D, E, and let's say this is connected like that. Okay, so a cut edge is basically cut edge, an edge upon removal of which the graph becomes fragmented. So in this uh, figure, can anyone say what is the cut edge in this? So what do you think if I remove this AB node? So let's say I remove this, the graph is still connected, therefore that is not a cut edge. Now if I remove this, the graph is still connected. Still connected graph means there exists a path from any two pair of, you pick any two random nodes from the graph and you will always get a path between those two nodes. In such a case it is connected. So uh, that is not possible when the graph is fragmented. So if I remove this edge between A and C, it does not affect the connectivity. Now if I remove B and C, it still remains. If I remove E and D, what do you think? The graph becomes fragmented or not?
Yes, sir, it becomes fragmented.
Right. And if I remove this, then if I remove
Yes, sir.
the,
Sir, it's
okay.
disconnected.
So this is the, these two are the cut edges. So this marked by cross, so cross represents cut edge. So these are the cut edges. Okay, so that is not the question that they have asked. So now they have told us that we have a graph G with m vertices. So what is the maximum possible number of cut edges in the graph? So they have not given us any specific graph. So they have just told us what is the maximum possible cut edges we can have in the graph. So first let us solve it part by part. A graph with m vertices can have maximum of how many components? A graph with m vertices can have a maximum of how many components? So by components, I means how many connected components it can have. So what do you think? Any graph with uh, m vertices can have how many components? Any guesses? It will have m components. So basically m components, which are the vertices themselves. So vertices themselves. So if you have a graph with no edges, so just the vertices, so that graph has m components, right? So now when we remove a cut edge, when we remove a cut edge, how many number of components are created? How many number of components do you think is created if we remove a cut edge? Imagine this figure. Take in this the graph that I have drawn. If I remove one of the cut edges, how many components will be created?
Sir, 2.
Right. So when we remove one cut edge, we are getting two. So we always get one. We always get uh, an extra component upon removing a cut edge. Means remove n cut edges, you will get n plus 1 components. Now a graph with m vertices will have a maximum of m components. So therefore the number of cut edges that you can remove are, what do you think from this last line? If you remove n cut edges, you will have n component. Now if I flip the question that you have m components, so to create m components, how many cut edges do we have to remove? Remove dash cut edges. What do you think?
M minus 1.
Right. So you will have to remove m minus 1. So since a graph can have maximum of m components, we can remove a maximum of m minus 1 cut edges. So right answer is option C for this question. I hope this is clear to everyone. Okay, then we'll move on to the next question. So again, let the number of cut vertices of the following graph be x and the number of cut edges be y. What is the value of x minus y? So we have discussed what cut edges are. So for cut vertices, so cut vertices are vertices upon removal of which the remaining graph remain uh, gets fragmented. So it's similar concept to the cut edge concept. So in the cut edge you remove the edge and you check whether the graph became fragmented or not. In vertices you remove the vertex and all its connected edges and check whether the remaining graph is fragmented or not. So I'll start one by one. So you have 8 vertices in this graph, in the graph shown. So you tell me which of these 8 are cut vertices. Okay, go ahead.
3 and
Can you repeat again?
3 and 5.
So you are saying that 3 is a cut vertex, right? So if you remove 3, you are left with 1 to 4 on one side and 5, 6, 7, 8 on one side. So and if you remove 5, so there is no connection between this 1, 2, 3, 4 and 6, 7, 8. So they are right. But if you remove this 2 also, you see that 1 gets fragmented out from the rest of the graph. So you have 1 and then you have 4, 3, 4, 5, 6, 7, 8. So 2 is also a cut vertex. So the number of cut vertex is 3. X equals to 3. What are the cut edges in this graph? Can anyone tell? Okay, so I'll go one by one. So what is the edge between 1 and 2? Is it a cut edge or not? So if I remove it, will the graph become fragmented or not?
Yes, it will become
So
fragmented.
right, so 1 and 2 is a cut edge. Between 2 and 3, what do you think?
No, sir.
Right, 2 and 4, 2 and
No,
4, right. Between 3 and 4,
no, no.
3 and 5,
Yes,
right. So it is a cut edge. Between 5 and 6,
no, sir.
6 and 7,
No,
5 and 8,
no,
5 and 7,
no,
and 7 and 8.
no.
Right, so you are right. So we have only two cut edges. So x and y, x minus y is basically 1. So right answer is option B, 1. I hope that is clear. It's pretty straightforward. Uh, Now come to the following question. So statement 1, Pn is a spanning subgraph of Kn and Cn is a spanning subgraph of Kn. So what does this symbol represent? Kn is uh, a graph with n vertices. Think a complete graph. Pn is a path with n vertices and Cn a cycle with n vertices. Now tell me, so what this statement 1 is saying, that Pn is a spanning subgraph of Kn. So you have a graph and Kn, that is a complete graph. So there is an edge between any two nodes in the graph. So any two pair of nodes you pick and there is an edge present. So that is the graph Kn. Pn is a spanning subgraph. So there is a path which is contains the n edges, n vertices, and it is a path. So uh, it is Pn a spanning subgraph of Kn. So you have this graph. I'll draw, let's say, a graph with 5 vertices. So the complete graph Kn would be like this. So this is the complete graph Kn. The blue edges are for Kn. Now tell me what is Pn. So Pn is, I can have any path. So let's say from, I'll name this nodes A, B, C, D, A. So it is a path of n edges. So let's say a path from uh, A to D. So we can have something like this: 1, 2, 3, 4, 5. Yeah. So this is a path. So this red is Pn, right? So is it a spanning subgraph? So Pn, this n represents that it contains n vertices and it is a path. So therefore you see that it contains a, all the vertices are covered. So therefore it has to be a spanning subgraph. And what they are asking is a spanning subgraph of Kn. So with n vertices, wait, for now come to Cn. So for Cn, what we'll do is this. So let's say from A to A, we'll have to create a cycle. So from A to A is basically like this. So we create, choose a different color. We go from A to B, B to C, C to D, D to E, and E to A. So this is Cn. It contains n vertices plus the starting. So again you see this Cn contains A, B, C, D and E, all the vertices. So it is again a spanning subgraph. So statement uh, 2 is also correct. So both the statements are true. So the right answer is option B. I hope this is clear to you. It's just some definitions. Okay, let us move on to the next question. So you have a set A which has walk, trail, path, cycle, circuit. Now a relation R is defined on the set A cross A such that the ordered pair A comma B are related if A always contains B. Which of the following elements exists in R? Now, what do you think of this question? So I'll just write it for definition. Wait, repeated uh, edge, repeat, repeated uh, edge. Now I'll write walk, trail and path. Now, okay, we'll have circuit and cycle. Now tell me, so a walk, does it have repeated vertices and repeated edges? What do you think? Yes or no?
Yes, sir.
It has both repeated vertices and repeated edge. What about a trail?
Only repeated vertices.
Right, so no repeated edge. And a path?
No repeated vertice or edge.
Right. Now for a circuit, like I mentioned, circuit is is a closed trail, which means the starting and the ending are the same, and a cycle is a closed path. So the circuit and a circuit and a cycle looks exactly like the trail and a path. So you have repeated vertices but no repeated edge. and in cycle neither repeated vertex nor repeated edge. By repeated vertex we are not counting the starting vertex twice, so excluding that there are no repetitions. So now tell me, so does a walk contain a trail? Come to option A. Look at option A. Does a walk contain a trail? What do you think? Which is the bigger set, trail or a walk?
Walk.
Right. So if you look at these three figures, sorry, these three rows, what you get is this, that you have this big set walk within which there is trail and within which there is path. So walk contains a trail, so A is definitely correct. About circuit and cycle, like I have mentioned before, so these also fall under trail. So a circuit will fall under a trail, and cycles will also fall under trail. So this is circuit which is contained within, uh, so you have like this. So you have circuit, this is circuit, and within which you have cycle. So path is different from circuit and cycle because path does not has is closed, so they are different. But trail can be closed or unclosed, it does not matter since the vertices can repeat. So this is the diagram. So looking at this diagram, now does cycle contain circuit? Is option B correct? What do you
No,
think of
sir.
option? Right, so because circuit is the bigger set and cycle is the smaller set. Similarly, option C, trail contains a path. As you can see, the trail is the bigger set and within which path is contained. So trail contains path. So option C is right. Does a trail contain a walk? So no, because walk is the bigger set and trail is the smaller set. So option D is also not right. So only A and C are the correct options, and as you can see it from the figure that I have drawn. I hope it is clear. Okay, coming to the final questions of our discussion. So select the set below which has the lowest sum of the number of cut vertices of both its element. So what do you think a graph kn? So before we solve it, look at the number of, uh, see all the uh, eight all the four options they have. So you have a k5, there is a uh, graph with with 5 nodes and a graph with 6 nodes. So which pair do you think has the least number of cut vertices? So now consider this kn. Let's say kn. Does it contain cut vertex? Does it contain cut vertices? What do you think? So to give you a picture again, I will draw this figure. Okay, I'll draw 4 vertex now to make it simpler for everyone. So this is your kn. So it has 4, so this is k4. Now what do you think? Does this contain any cut vertex? Can this graph contain a cut vertex? Kn by definition is a complete graph, so it means that all edges are connected with, all nodes are connected with each other. So if I remove one of the vertex, what will happen to the other vertices? Will they remain connected with each other?
Yes, sir, they will remain connected.
Yeah, by definition, since it's a complete graph, the other nodes will still remain connected with each other, so it cannot contain a cut vertex. So if I remove any one of the nodes, the graph does not become fragmented in Kn, so it does not contain cut vertex. What about Pn? Does it contain cut vertices? Let's say, so I'll draw again 4. So let's say this is your path. uh, okay, so let's say this is your P4. How many cut vertices are there in this graph? So,
Sir, 2.
right, so if I remove this, it becomes fragmented. If I remove this, it becomes fragmented. So it is basically the in between elements that would be present. So it will, a path Pn will have n minus 2 cut vertices. Now come to Cn. So Cn is basically again same question, does it contain cut vertices? So I'll draw Cn like this: 1, 2, 3, 4. So you have C4. Now tell me, does this contain a cut vertex or not?
No cut vertex, sir.
Right, a cycle does not contain cut vertex. No cut vertex. You can have a different cycle as well, so maybe you go from here to here and here. This also does not have a cut vertex, so only Pn among the three has cut vertices. So the which set below has the lowest sum number of cut vertices. So basically the simple answer is which has the lowest number of, so which does not have Pn or the lowest number. So in this option A does not have any Pn, doesn't have Pn, therefore it has the lowest number of cut vertices. Others will have uh, 4 cut vertices because P6 will have n minus 2, so you have n minus 2 cut vertices. So K5 will have no cut vertex, P6 will have 4. It is, so I'll write 0 plus 4. C5 will again have 0 cut vertices, but P6 will have 4, and P5 will have how many? 3, and it will have 4. So here it is 0 plus 0, 0 plus 0. So that's why option A is the right answer for this question. I hope this is clear to everyone. So that brings us to the end of our discussion. So if you have any questions regarding the problems that we discussed, you can ask, or if you have missed anything during the discussion, I can repeat it, or Anyone, any doubt? Okay, if not, then I think we can conclude the session for today. So again, there will be a TA session tomorrow at the same time, and similar topics will be discussed, but different questions will be discussed. And if not, then we'll meet again next week at the same time, and we'll discuss week 8 questions. So if no one has any questions, then we can close the session for today. All the best everyone for your time, and wish you best of luck for this course. Thank you everyone.